Sorry about the that. So hello and welcome everyone. So today webinar is based on Rohde and Schwarz advanced de-embedding techniques and with the vector network analyzer. I'm Mahwash Arjumand, application engineer in Rohde and Schwarz, Canada. I'm looking after the RF and microwave test equipments, and one of my specialties are vector network analyzers. Here's the agenda for our webinar today. First, we will go through the fundamentals about the vector network analyzers and the measurements that it takes. And then we will go through the system error correction or the calibration, which is one of the main topics about the VNAs. Then we will see what is de-embedding and what are the possible de-embedding solutions. After that, we will go through the advanced de-embedding techniques that Rohde and Schwarz offers. And then at the end, we will have a live demo of de-embedding a PCB structure with our vector network analyzer, ZNA. So to start with, vector network analyzer is basically a test instrument that actually measures the properties of physical components like devices. For example, filters, cables, amplifiers, mixers, attenuators, anything. The main thing or important thing about the vector network analyzer is that it has the internal source and also the receiver. So basically, the VNA generates a stimulus that is provided to the component or our device under test. And the same box measures the response of the devices. In terms of measurements, what it measures, basically, it can measure the magnitude and phase of our devices. It typically gives you the forward transfer function of your components, and also it gives the information about the reflection coefficients. The VNAs can be swept in frequency, and most of the modern VNAs also have the capability to be swept in power, which is very useful for active devices measurement, for example, amplifiers. So we can measure amplifiers in the power sweep range, seeing the compression point or the P out versus P in curve. So where these vector network analyzers are used, the main uh, is that they are capable of doing the S parameter measurements of the devices, both the active devices and the passive devices. They are nowadays are mainly used in the high-speed signal integrity applications. They can also do the time domain measurements as well. They are also utilized in load pull systems as well. They are also capable of doing the material measurements as well. For example, analyzing the behavior of the material, their permeability and permittivity. They are also capable of doing the group delay measurements or the phase delay measurements. So these are the different core applications for the vector network analyzers. Now let's see how the network analyzer works. So here we have a source that will basically generate the incident wave, which will be through the port 1. And inside the vector network analyzer, we have a directional coupler, basically. And this coupler will separate the incident wave, and it will go into the measurement receiver, which is also inside the vector network analyzer. The signal incident wave will go to the device under test, and the reflected part of the reflected wave will come back to the port 1 in the measurement receiver, and then we can measure the reflected B wave of our device under test. And of course, the most part of the signal will pass through the device under test, and after passing through the device under test, it will go into the measurement receiver of our port 2. And in this way, we can see the behavior, transmission behavior of our DUT. The same goes when the stimulus is generated through the port 2, seeing the reflection behavior at the port 2 of our component and analyzing the reverse transmission behavior at the port 1 of our device under test. After this test set, the signal is processed and displayed on the vector network analyzer. So now we have seen fundamentally that VNAs can generate the incident waves and measure the forward transmission or the reverse transmission B waves. We come across very commonly when we talk about the VNA, the S parameters. So the S parameters are nothing but the ratio of those wave quantities that VNAs work with. So if we talk about the incident wave, which is applied at the port 1 of our device under test, that would be A1. And the same incident wave passes through the device under test, and we measure the response of our component, which will be B2. So the ratio of this response, which is B2, divided by the incident wave A1, would be our S21 parameter, which is the forward transmission measurement. And if we talk about the reflection measurement, then the part of the signal which is applied over here at port 1, for example, would be reflected back, will be measured as B1, and to differentiate it, we will say reverse. So the ratio of this B1 reverse signal versus the incident wave A1 would give us the reflection parameter, which is S11 in this case. And if we talk about putting the incident wave from the port 2, it will be the same thing, which will be S12 and S22 at the port 2. So based on this two-port simple uh, device under test or the component, we will get all the 4 S parameters in terms of incident waves and the reflected waves for complete device characterization. When we see this as parameters over here, the numbering over here actually tells us that from which port the stimulus is applied and on which port the response has been observed. So if we talk about this later number over here, this is the port which is generating the stimulus. And the first number over here basically denotes that port 2 is receiving the signal. So this is how basically the VNA is calculating the S parameters and giving the characterization of our components. When we talk about the network analyzers, we know that inside the network analyzers, there are different components. For example, there is a direction coupler, there is a VSWR bridge. So all these components basically have some inaccuracies. They are not ideal components. Also, to connect our device under test, we need cables in our test setup for the connection. So the components inside the vector network analyzer and the test setup, which could be the cables or any additional connectors or adapters that are required to connect the devices, are utilized. We need to see the response of our device under test. So that's why the calibration or to reduce the effect of all this test setup is necessary. For this, we perform the system error correction so that any internal component effects of the VNA and the cable effects or the connector effects could be taken care of. So usually we do this with our calibration standards, open through short and match. And these standards are known data and all these known data is actually inside the vector network analyzer. And then when we connect these known standards at the end of our cable on from which usually we connect our components, and we perform the calibration, the VNA internally calculates with the known data of these standards, and all the effects of the internal components and the cables is removed. So then our calibration plane would be at the end of the cables instead of at the end of the VNA ports. We can also achieve this by using the automatic calibration unit available, which actually reduces the time of performing the calibration drastically. So we have seen the VNA as parameters and the system error correction. Now we will go through the de-embedding and the possible de-embedding solutions, which are part of the RNS VNAs as a standard. So what if we have the scenario on which our device under test is on a PCB, and the access to the device under test is not through the coaxial connectors. It's fabricated on the PCB, and it has the connectors at the end of the board. When we perform the calibration is usually done at the end of the cables as discussed in our previous slide. So this is our calibration plane over here. We need to measure the response of our device under test. So our desired measurement plane should be at the device under test. So we need to remove the effect of these traces, uh, which is on the fixture. So here um, the de-embedding role comes into play, that we have to de-embed this um, traces on the PCB board to get exactly the response of our DUT. For this, there are a couple of different methods that is available on the vector network analyzers. The first one, which is commonly known as offset compensation or the port expansion. This offset compensation is available as a standard with our RNS VNAs. So what it does is basically, for example, if we talk about an short over here, we all know that the short has some offset inside it. So when we will connect this short standard, you will see an arc on the Smith chart like this. It's because of some offset length that is present inside the short standard. With the press of the button on the VNA for the offset compensation, basically, so we can actually reduce or remove this effect of this offset over here. With the press of the button, it actually calculates the delay, the VNA itself. And here you can see it gives us a nice result of the perfect short instead of having the arc on the Smith chart. So this is one of the basic tools for the de-embedding. The thing is that this tool is usually works good up till 5 and 6 gigahertz. So above that, the results are not too much accurate. The another method or the possible for the de-embedding we can use is the time domain gating. So for example, over here, what I did, there is a transmission line over here, and my DUT is from here till here. So I have some lead out and lead in structures and this connectors as well, coaxial connectors. So if you connect this device and see the reflection or S11, you will see this blue trace over here is the response. So in the time domain gating solution, what you have to do is basically you have to convert this frequency domain into the time domain first. So because most of the VNAs are capable to do the time domain measurements, it's one of the solution that could be utilized. So when we convert this frequency domain measurements or the frequency response into the time domain, we can see over here this blue trace. So over here, you can see this is the behavior of the connector, which is coaxial over here. And we have some transmission line characteristic over here. And again, a bump. So this is our lead in. And then over here, it's our transmission line, which is our device under test, which displays this. And then we have our lead out and the connector response, which is from here to here. So in this, what you have to do, actually, you can apply a time gating, and you have to tell the VNA yourself that at which part you want to look into. So by seeing this response and our device under test, we can somehow figure it out that this part over here is the connector and the lead in response. And this part over here is the connector and the lead out response. So what I did, I applied the time gating on this nice transmission line characteristic over here. And after applying the time gating, we have to convert this time gated measurement again back to the frequency response, which will be the time gated S11. And you can see over here, this green trace is basically the time gated response of our transmission line only. And you can see that we have improved the reflection by just removing the effects of the connector and the lead in and the connector and the lead out. So there are 4 steps involved in this. In this method, you can actually have to give or tell the VNA which part of the measurement you need to apply for the time gate. Also, there will be only the reflection data, no insertion loss data. So in this solution, you cannot actually fully characterize your device under test. It will give you only the information about the return loss. The another method is the TRL calibration. So in the TRL calibration, we have our device under test, and we need to have the coupons or the same fixture, which actually represents the line of this PCB board. So we have a through, and then in this TRL calibration, we also need to define different line standards because the through actually does not compensate for the complete characterization of this board. So for example, if your DUT is going higher in frequencies, then you need different line structures for different frequency ranges to characterize for the complete frequency band. Also, in the lower frequencies, you also need a match standard as well. So in this TRI calibration, you need to have like different coupons to characterize it. And also these standards need to be very similar in characteristic of actual fixture plus DUT. So if there is any differences in the impedance, which will be this TLA calibration does not give the accurate results. So these methods, which could be the mainly used previously have different caveats or the limitations of using it. Now we will go through the advanced de-embedding and fixture modeling. So if we talk about the advanced de-embedding in the TRL calibration, what we have seen that we need too many standards to get the calibration correct. And also for designing those standards, we need to be very careful to have the impedances as similar as the fixture plus dot. This is practically very difficult to have those standards made with the similar impedances. There's always some differences in the impedances of the PCB boards, and therefore the results are not that accurate. And because of this inaccuracies, this advanced fixture de-embedding comes into play. So basically, in this de-embedding algorithm that runs could also correct for the impedances um, between the test coupons and the fixture plus the dot. And in this de-embedding, you do not need to have like 3 or 4 different standards depending upon the frequency. Only one test coupon could be enough. Either you can have 2 into through, or 1 into open, or 1 into short. And this, for example, if we talk about this 2 into through, with this advanced de-embedding algorithm, the effect of these traces would be removed from the result, and you will get the response of over the dot only. Talking about the coupons and designing of it, there is an IEEE 370 standard. It's a very good document, basically, and it actually provides very detailed specification and requirements in terms of fixture design and electrical requirements of the fixture. For example, over here, this is the screenshot I have taken from this standards document. And it actually tells that how you have to design the through coupon. So for example, for the through coupon, the insertion loss could be -10, -15, or -15 again. In this IEEE standard, basically for these coupons, they have characterized them in 3 different classes, known as class A, class B, and class C. So what are the difference in between these classes is, you can see the difference in the insertion loss, return loss, and difference between the insertion and return loss, crosstalk, and impedance variation, and all those different things which is needed to design the coupon. So for example, you can see over here, the class A, the design requirements is kind of very strict. And as we go further into the classes, for example, class B or class C, there's a kind of a relaxed design requirements for the coupons. When we talk about these classes, so we classify, okay, class A has the most stringent design requirements. Class B is okay in between class A and class C, and class C is the least stringent design requirements. So this classes comes into play when we talk about the coupons. Now, if we have these different classes of the coupons and the de-embedding, of course, the de-embedding would be different with all these specifications of the coupons. Then what comes into play is the de-embedding tool, like the advanced de-embedding tool that actually corrects for these coupons behavior. So when we have our class A, because it is so nicely designed, the de-embedding tool could be less sophisticated that can handle these great designed coupons. And if the coupons lie between in class C, then the tool has to be a very good software algorithm running that can actually handle these lower design requirements of the class C. So this is we have to be careful when we will be designing the test coupons. Now, the advanced de-embedding techniques that is available with Rohde and Schwarz are four different. The good thing is that our these three, which is EZD, ISD, and SFD, these all three tools actually supports all the three classes of the coupons requirement, and it is as per the IEEE 370 standard. This delta L is on the specifications of the Intel based as well. So we cover the Intel specifications and IEEE 370 standard as well. So all the four tools are available. These are all very good integrated in our VNA or models, and there is no need to install any external software on the VNA or on the PC. It runs into firmware integrated, and you can measure the coupons two into through, one into open, or one into short. Or you can actually, if you have the S2P file, you can load it into these tools and measure your fixture plus DUT and get the results. So if we see the process flow of our de-embedding technique, it's very easy. So first, we have to perform the calibration, the regular calibration at the end of the cables. And then we measure the test coupons, whatever it would be. So our test coupons, as discussed, could be two into through or one into open or short. And after measuring the coupons, you can measure the complete structure with the dot and the fixture. And then simply with the click of the button, you can run the fixture modeling tool, and the results of the DUT is calculated and displayed. So this screenshot over here is from our software tool, de-embedding tool, which is very simple. So it's a two-step. You can actually select from here what type of coupon you're using. You can either measure the coupon by connecting it through the VNA directly, or if you have the S2P file, you can load the S2P file. And then you connect a fixture plus DUT, and you can measure it. And then after hitting the apply button, the software algorithm runs in behind and compensates for this coupon, which was measured earlier. And you can see over here the impedance correction as well. So you can turn it on, and the software algorithm will run the impedance correction for the coupon and the fixture plus DUT as well. So we have talked about the advanced de-embedding and how easy it is. Now the question comes that what could be the possible use cases to when we need these de-embedding tools or techniques. So the one could be the PCB. We have a device under test on the PCB board, and there is no coaxial connectors on the PCB. So the probing is done on the PCB. Usually, sorry, our reference plane is at the end of the cables, and we need to um, measure the device under test over here. So we have to compensate for this lead in and lead out. Then with the two into through or the S2P files, we can actually have this lead in and lead out structures de-embedded, and the result only for the device under test. The another use case could be that uh, you need to measure the connector. For example, over here, it's a PCIe Gen 5, and we have a baseboard and the add-in card for the PCIe. So this is the PCIe connector, which needs to be measured, and we need to uh, de-embed this lead in and the add-in card or the lead out. So on the board, you can see over here, this will be done with the two into through. So we have the two into through. We can measure this two into through and compensate for this lead in and lead out structures. Another possible case would be the cable test. So we have, for example, over here, this is the USB Type-C cable test fixture. So this is our cable. The area of interest is over here, but we don't have cannot connect this USB Type-C directly to the VNA. So there is a fixture with the coaxial connectors. So basically, we have to de-embed this fixture at the input and the output. And this could be done with our different de-embedding techniques. Over here, you can see we are using our multi-port vector network analyzer, which is uh, handy because we have uh, 8 or 9 ports for this USB-C type cable testing. Uh, you can do this with a 4-port vector network analyzer as well, but of course, you have to connect and reconnect the connectors over here to perform all the measurements. But with this multi-port VNA, you can do all the measurements and the crosstalk at the same time. Another use case would be the chip, or we usually say system on chip SoC test. We have the oscilloscope over here to see the response, and we need to measure this silicon package, which is on the chip. And we need to basically de-embed this lead-in structure. So with the help of the vector network analyzer and de-embedding techniques, we can actually measure um, this lead-in and import the S2P file on the oscilloscope and have our results for this package under test. And the most common use case is the RF devices, which is on the PCB, and we cannot directly access these device under test. The connectors are at the end of the PCB board, and we have to de-embed these lines over here. So then we measure this two into through, which is on the board. And by measuring this two into through, this two into through will be de-embedded for these leads and leads out the structure, and the device and the test would be measured. So these are a few possible cases commonly seen, and with these cases, the de-embedding techniques could be utilized. So we now have the demo. Before I start the live demo of the de-embedding, this is the board which I will be using for our live demonstration. On this board, it's basically I have the single-ended structure. And over here you can see this is the coupon or 2 into through I have. Over here, I have the one into open as well. The short is not populated, so we will not be using it. I will only be using the 2 into through coupon. And then on this board, I have two types of device under test. So this DUT, which is named as 1A, is a simple transmission line of 50 ohms. And the lead in and lead out structure is also 50 ohms. But this another device, which is named as 1B, is kind of interesting over here. So I have this transmission line, which is my area of interest or device under test. And you can see the lead in and lead out is deliberately designed with different impedances as the transmission line. So our transmission line is of 50 ohms, and we have a lead in, which is around 52.5, and lead out, which is 47.5. So basically, this gives a very good idea, or we can see how fine our RNS de-embedding technique is, which will actually compensate for this impedance mismatches as well. And the 2 into 3 is, of course, the 50 ohms. So this is the test setup, which I will be using for the demonstration. So it's a single-ended, so I'll be using port 1 and port 2 of vector network analyzer. The model I'm using is ZNA 43, 4-port. This test setup I have already calibrated till the end of the k-pills over here using the automatic cal unit, which is ZNZ54. So I have calibrated from this frequency range. I have calibrated port 1 and port 2, which is unknown through, open, short, and match through this calibration. And you can see over here, we have a cal indication. That means our active channel is UOSM calibrated between port 1 and port 2. So the coupon, which I showed, the 2 into through coupon over here, this is the response or the result of the coupon. We were discussing about the different classes as per the IEEE standard. So for example, if we see the insertion loss and the return loss of the 2 into through, the class A says it could be minus 10 dB or better, minus 15 or minus 15. So over here you can see this is the basically the insertion loss of the 2 into through, which we will be using to de-embed the lead in and lead out structures. And this is the return loss. So I have put the marker at 35 gigahertz. And you can see that these two traces actually well apart. These are good up to 40 gigahertz, the test coupon. And this is the basically the impedance response of our 2 into through. So over here, I will also do the live demo, but I have just put like the few screenshots. On the demo board, I will be measuring device named as 1B. and it has a 50 ohm transmission line, and it has a different impedance of lead in and lead out structures. So basically, this is the response of our fixture plus DUT before de-embedding. So we have still not applied the 2 into through de-embedding, and you can see the return loss and insertion loss of DUT plus fixture. Now, in this slide, I have attached a screenshot. It's the same device in the test I'm measuring. And basically, this screenshot is giving us the comparison of the results of the insertion loss and the return loss before and after the embedding. So what I did basically, before applying the de-embedding, I put these traces into the memory. So the memory traces are the results before de-embedding. And then I measured the 2 into through and run the tool. And I got these traces, trace 1 and trace 2, after the de-embedding. And you can see how the insertion loss has improved because the lead and lead out structures from our device under test has been removed, and also the return loss is improved. So let's see the live demo. This is the setup I'm currently using, and we can go through our software tools. So I will stop sharing from here. I have my ZNA remotely, and I will share the screen of ZNA. So sure. Okay. You guys can see the screen?
Yes.
Okay, perfect.
Thank you.
So these measurements are already done. What I will do, I will preset the ZNA. So we start from the scratch. um, uh, I don't want to redo the connections again. So what I did, I actually did a calibration and saved the file. So if I go into the file, I have port 1 and port 2 calibrated from 50 megahertz to 40 gigahertz. So I will simply recall this calibrated file. Um, and then right now, the DUT1B, which is a transmission line with different impedances of lead in and lead out, is attached. So we can see this is the insertion loss of this. So what I will do before doing the de-embedding, I will add more traces. So I will simply click over here to add the trace. Um, and I will drop at the bottom, and I will look into S11. And then this S11 we can change into uh, impedance response. So in the measure, I can go and I can change this to the impedance response. Now you can see the scaling over here is changed into ohms instead of the dB. And then I can see this impedance response in the time domain to have a clear picture. So I will go into the measure. I will go into the time domain, change into the step response, and then I will simply turn on the time domain. So this is the time domain response, and I will go into scale, auto scale the trace. So you can see over here, this is looking like the connector, and then lead in and some our transmission line, and then lead out. Uh, so this is basically the impedance response of our completed structure. Also, what we can do is over here, I can say simply the return loss. And then in the offset de-embed menu, we go over here and under the de-embed assistant. This actually allows us to select what different type of duties you have. So we can also measure multi-port duties. We can also measure the balance duties. So there is a whole lot of different choice of the that available with this de-embedding tool. I'm using in situ de-embedding tool right now. Our device is very simple, 1-into-1 single-ended, so I will leave over there. And then press next. We have on our demo board the 2-into-through coupon. Simply define port 1 is connected and port 2 is connected. So this tool basically allows us to measure the coupon's life, or you can load the S2P file. I have already measured and saved the S2P file, so I'll simply go over there. This is the demo board 1 through S2P file. I'll simply recall this. So you see it marks it as a green. And then I will turn on the impedance correction. Uh, and I have the fixture plus DUT already attached with the VNA. So I will simply, in the next step, press measure. So it measures my DUT and the fixture. And this apply button over here, when I will press this, it will run the software algorithm. And it will take around 40 to 45 seconds. And the de-embedding will be done. So all done. And then we can close over here, and you can see the response of our device under test. So to compare the results, I can turn off the de-embedding, and I can put the traces into memory. So over here, memory, and then I can go into de-embed, de-embed, and I can simply turn on the de-embedding again. And you can see the insertion loss is improved, the return loss is improved, and this gives us the clear picture over here. You can see this blue trace over here was actually the effect of the connector. This response of the lead in is removed. So, and the lead out connector is removed, and the green trace is basically giving us only the DUT. So this how the de-embedding works, and you guys can see the effect of this tool. It actually does apply the impedance correction as well, and the responses of the lead and lead out has been eliminated. We can also do one thing. So what I can do, just to show you guys, I'm removing this. So this is the impedance corrected de-embedding. What I will do, I will put this into the memory, and I'll go again for the offset de-embed. de-embed assistant. And next, and then I will simply load again the demo board. So right now what I'm doing, I'm turning off this impedance correction, and I will simply hit apply. Just press yes, and the tool will run again, but this time it will not correct for the impedance mismatch. So I just want to show you guys how this impedance correction affects our measurement results. It will again take 40 to 45 seconds to run the tool. Okay, so this is done, and I will close it, and you can see. So this green trace is the de-embedding done without the impedance correction, and this blue trace is actually with the impedance correction. Because our DUT has the lead and lead outer structures with different impedance, and you can see actually uh, the effect on our measurement results with the impedance correction and without the impedance correction. So, yep, this is all the live demo I had to show the results of the de-embedding and with and without impedance correction utilized.